Let's find some more antiderivatives. Let's find the antiderivative of 13 minus x dx. So the antiderivative of the 13 will be a 13x, and the antiderivative of the x will be add 1 to the exponent, divide by the new exponent, plus your constant of integration. We'll check by taking the derivative. So the derivative of 13x is just 13. Bring down that exponent. And the derivative of the constant is just 0. So we get 13 minus x, which is the integrand. So happy times, we got the right antiderivative. Alright, how about 8x cubed minus 9x squared plus 4? And we're going to take the antiderivative of that. And if you want to pause the video and try it on your own, go ahead. Alright, now you can check. So add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the exponent. Add 1 to the exponent, and divide by the new exponent, plus your constant of integration. And then we'll go ahead and reduce. So 2x to the 4th minus minus 3x cubed plus 4x. And plus your constant of integration, and then we'll just go ahead and check by taking the derivative and see if we get the integrand. So when we take the derivative of 2x to the 4th, that 4 is going to come down and become 2 times 4, which is 8. Subtract 1 from the exponent, 8x cubed, minus the 3 comes down. And we'll subtract 1 from my exponent, and it looks like in the excitement I didn't write down this correctly, so let's fix that. So 3 times 3 is 9. Okay, and then derivative of 4x is just 4, derivative of the constant is 0. And we do get the original integrand, and we have correctly found it. Found the antiderivative. Alright, let's do a couple more. We'll do some more exciting examples. So to find the antiderivative of square root of x plus 1 divided by 2 square root of x dx. And we need to make this a little bit more user-friendly so we can see the exponents. So this is x to the 1/2 plus a half, and then since it's the denominator, x to the minus 1/2 dx. So we're just going to add 1 to those exponents and divide them. So that becomes 3/2, divide by the 3/2. Pre-existing 1/2 is hanging out in front. Add 1 to the exponent, becomes 1/2. Divide by that new exponent of 1/2. And don't forget your constant of integration. So when we divide by fractions, we flip them. So 2/3 x to the 3/2, the 1/2 will cancel. We'll have x to the 1/2 plus the constant of integration. And then we just need to check to make sure that we actually did find the correct derivative. Not derivative, correct antiderivative. And so what we'll do is we'll use the power rule. So we have pre-existing 2/3, bring down that exponent, 3/2, subtract 1 from your exponent, becomes x to the 1/2, plus bring down that exponent of 1/2, subtract 1 from it, and you get minus 1/2 as the exponent. And we'll rewrite. So the 2/3 and the 3/2 take care of each other, and rewriting without the negative exponent. And we have the original integrand, so we have correctly found the antiderivative. Okay. Before we get into a couple more examples, we'll do a little bit of trig. So trig's always fun and exciting. And the derivative of the sine x is going to be the cosine. So when we take the antiderivative of the cosine, we're going to get back the sine plus a constant of integration. And take the derivative of the cosine, and we'll get minus sine. So derivative of cosine is minus sign. Alright. And when I take the antiderivative of the minus sign, I get cosine x plus constant of integration. Take the derivative of the tan, and we should get secant squared. So the derivative of the tan is secant squared. And so when we take the antiderivative of the secant squared, we'll get back to the tan plus of constant of integration. Okay, what about if we take the derivative of the secant? Derivative of the secant is going to be secant x tan x. And so when I take the antiderivative of the secant x tan x, I'll get back to secant x plus a constant of integration. Okay, and then similarly, you can get these other ones. So find the antiderivative of negative cosecant cotan, and that'll be back to the cotan. I'm sorry, I think I have it the reverse. I can't see it. Negative cosecant cotan x is equal to, antiderivative of negative cosecant cotan x is equal to the cosecant plus c. And then, I thought I did that one first, antiderivative of negative cosecant squared dx, that's going to be your cotan x plus c. Okay, so if you know your derivatives, you can always go backwards with and find those antiderivatives. I remember this little ladder for the sine and the cosine. So the derivative of sine is cosine, the derivative of cosine is minus sine, derivative of minus sine is minus cosine, and then the pattern's going to repeat. So to go down the ladder, we take the derivative. To go up the ladder, we integrate or find the antiderivative, and this pattern's just going to repeat. So then we get sine x and cosine x, and you can go as far as you want in both directions. Okay. So how about the antiderivative of t squared minus cosine t dt? So we're going to add 1 to our exponent, divide by our exponent, and then antiderivative of cosine is sine plus constant of integration. And then we'll check by taking the derivative of not dx, but dt. And that'll be add 1 to the exponent, divide by the exponent. Now bring down that exponent, Bring down that exponent, so the 3's are going to cancel, and you'll have t squared. Derivative of sine is cosine. And that does equal our integrand. Okay. And then we'll look at the antiderivative of theta squared minus the secant squared theta d theta. So we'll add 1 to our exponent, divide by our exponent, and the derivative of tan is secant squared. So to go backwards, the antiderivative of secant squared will be the tan. And of course, plus constant of integration. And we'll take the derivative. So that 3 is going to come down to cancel the 3. And derivative of tan is secant squared. Derivative of the constant is 0. And we do get, in fact, back to our integrand. So we know we've correctly found that antiderivative. Okay, let's look a couple more. I think I got 3 more. How about the antiderivative of secant y times secant y minus tan y? So I don't know what the antiderivative of secant y is yet. We're going to have to go a little bit further, get into like the natural log or something like that. That we're going to have to do some little clever tricks later with the natural log. Right now, I can distribute the secant and get secant squared y minus secant y tan y. And I know what those are. I know that tan has derivative of secant squared, and I know the derivative of secant is secant tan. Okay, so that gives me tan y minus secant y plus a constant of integration, and then just for completeness, we'll take derivative and make sure that those are what we said they were. Okay, so derivative of the tan is a secant squared, and the derivative of secant is secant tan, and the derivative of constant is 0. So we get back to the original integrand, and so we do have the correct antiderivative. Okay, and we're going to solve a couple of I guess we're going to find the particular solution for some antiderivatives. So find the particular solution. So maybe we know, for instance, that velocity is equal to 4x cubed. That's our velocity equation. And then I don't know about negative time, but we have an initial condition at -1. The output is 3. So we're going to take the antiderivative to get to g. So when we do that, add 1 to the exponent, divide by the exponent, add your constant of integration, and we got some initial conditions, which is going to allow us to find what the c is. So we'll have a particular solution. So g of -1 for our position function, -1 to the 4th, plus c equals to 3, so the c must be 2 in order to satisfy that equation. So our position function is x to the 4th plus 2. Okay. All right, one more. Let's say that the second derivative, our acceleration, is determined by the sine of x, and we have initial conditions that our initial speed is 1 and our initial position is 6. So we'll take the antiderivative of the second derivative to get to the first derivative. So antiderivative of sine is minus cosine plus constant of integration. And we have initial velocity is 1, so we're going to plug that in. Cosine of 0 plus c. Cosine of 0 is 1, so we have -1 plus c is equal to 1, so the c must be 2. So our velocity equation is minus cosine of x plus 2. And to find the position function, we need to take the antiderivative of velocity. So antiderivative of negative cosine x plus 2 is equal to negative sine x plus 2x plus a new constant of integration. We can call it c again if we want to. Our initial position is 6, so negative sine of 0, which is just 0, plus 2 times 0, which is also 0. So our c has to be 6. There's no choice. And so our original position function is negative sine x plus 2x plus 6. And there we have it.